What if the very idea of scarcity, of limits to human endeavor, was simply a terrestrial illusion? A whisper from the cosmos suggests a future where humanity wields energy on a scale barely conceived. It speaks of power-scale power, 1,000 times our current global consumption, not as a dream, but as a declaration. At the heart of this impossible vision lies the moon. Envisioned by Elon Musk, it transforms into the ultimate launchpad, freeing us from the constraints of Earth. This is not mere expansion, it's a redefinition of what civilization truly means. But how can a barren world become the wellspring of such immense power? The answer points to a colossal unrolled linear synchronous motor, the lunar mass driver. Leveraging the moon's weak gravity, this system electromagnetically hurls materials into space at extreme velocities, rendering disposable rockets obsolete. Engineering studies, dating back to the 1970s, confirm its physical possibility. Yet its realization demands an unprecedented leap of ingenuity. Superconducting magnets, mounted on a reusable bucket, interact with sequential electromagnetic stator coils embedded within an aluminum guideway. This is applied maglev, eliminating friction and wear, propelling payloads to the moon's escape velocity of 2.4 kilometers per second over remarkably short distances. Crucially, without an atmosphere, there is no air friction, no heating from resistance. The bucket itself endures hundreds of Gs, manageable for cargo, but not for flesh. Upon deployment, kinetic energy from deceleration is recovered, feeding back into the power grid, a closed-loop system echoing the cosmic cycles of creation. But the elegance of the concept hides a brutal reality. This grand endeavor grapples with physics at its extremes. The power infrastructure alone demands enormous energy bursts in milliseconds. For smaller payloads, a dedicated solar-based power plant of 8.7 to 20 megawatts is needed. For industrial operations, continuous nuclear reactors around 200 megawatts are required. This necessitates massive pulse power infrastructure, with advanced capacitor banks surging to an instantaneous 16 gigawatts during peak acceleration, a consumption comparable to a major city. The electromagnetic launch process generates extreme heat, soaring to nearly 800 degrees Celsius. Active cooling systems for both track and buckets are paramount, requiring radiator panels covering tens of thousands of square meters to dissipate this thermal burden into the vacuum. The superconducting magnets, meanwhile, demand cryogenic temperatures around -452 degrees Fahrenheit, maintained by liquid helium cooling. The moon's environment poses its own existential dread. Thermal expansion and contraction distort track straightness over kilometers, necessitating burial under lunar regolith for thermal and radiation shielding. Construction tolerances forbid imperfection, demanding sub-millimeter precision across kilometers, employing optical alignment targets and laser tracking, while passive magnetic damping sections absorb vibrations before they become catastrophic instabilities. Building such a monumental system relies on Starship's capability to deliver 80 to 100 tons of cargo per mission. Initial landings will establish basic survival infrastructure, temporary habitats, and an interim nuclear reactor for construction power. This will pave the way for heavy-duty tractors, robotic excavators, and soil blowers to prepare the lunar terrain, while critical components like superconducting ribbons will initially be imported from Earth. The ultimate vision is a self-sustaining lunar industrial ecosystem. In-situ resource utilization of lunar regolith, rich in aluminum, iron, titanium, and silica, will transform the moon into a manufacturing hub, producing structural components, electromagnetic coils, and even solar panel arrays. It is a testament to humanity's relentless drive to transcend. If a civilization can create its own sun from the dust of another world, what then becomes of the very limits we once believed defined us?